Dear colleagues, today I will present you my software GeoSpring 1.0. So this software was developed for the design of shallow and deep foundations. As you see, the development of such a product has started since 2015. So today we will see the futures of GeoSpring in the design of shallow and deep foundations. So let's go ahead. Basically, GeoSpring, it contains 4 modules. The first module, it's about the design of shallow and deep foundations. So it computes the bearing capacity and settlement. The second module, it's about pile foundations. So it computes the settlement of pilot foundations, single piles and group of piles also. The third module, it's about the design of rigid enclosures. And the final module, it's about the settlement of embankments. So the short-term and long-term settlement of embankments. So let us start by the first module. It's the footing module. So here we go here, for example, footing, short-term settlement. So here actually we have 2 methods: the deformation moduli method and the pressure meter method. So the user can choose, for example, deformation moduli. So here you have the thickness of each layer and the layer type. For example, let us say here you will have coarse sand and gravels, first layer, and the second layer will be, for example, silt. Okay, so here you will insert the thickness of each layer, for example 5 and 5. Here you will insert the value of the deformation modulus. Okay, I don't like to say Young modulus because in soils it will be more interesting to talk about deformation modulus, as the Young modulus is measured without a confining pressure. So here the module of the first layer, for example, 10 MPa, and the silty layer will have a module of 25 MPa. Here we can put 0.33 and here 0.35. Okay, so here you will insert the geometry of your footing. Okay, for example, it's a 3 by 3 square footing. The applied stress, for example, it's 150 kPa, the embedment 2, and the water table, for example, 2. Here simply you will push on this button and you will have the distribution of the short-term settlement along the footing width. So as we see, the footing width, it's equal to 3 here. So when you come back here, you will see that the settlement is at its maximum in the middle of the footing width, and it decreases along the footing width at the right and at the left side of the footing. Of course, when the behavior of the footing is perfectly rigid and it's not flexible, you will just take the maximum value of the settlement, which will be 2.5 centimeters. So let's move on to the metric settlement. We can go to the short-term settlement estimation by means of using the pressure meter data. Okay, so you open here pressure meter data. You put here, for example, the thicknesses of the layers, for example 5 and 7, and here you will put the pressure meter modulus and the limit pressure modulus, PMT data. Okay, let us say here that, for example, it's 200, and here it's, for example, 20, 25, 210, 250, 20, 20, 20. To accelerate, I'll just use like ordinary values: 250, 250, 250, 250, 250, 250, and 250. Here you will insert the geometry of your footing. Okay, for example, 2.5 and 3, Here you will insert the applied stress, the embedment of the footing, and the water level. Of course, here when you will insert the PMT data, pressure meter modulus, limit pressure, and the depth, you will insert these values beneath the footing. Let us say if the embedment equal to 3, you will just start to insert the pressure meter data from 3 meters of depth of the drilling PMT results. Okay, here you will push this button, you will take the short term settlement along the footing width. Okay, it will be more interesting to study the behavior of a group of footings by means of these data. Okay, footings group. But before going to footings group here to estimate the short-term settlement and odometric settlement, we'll just go rapidly to see the estimation of the odometric settlement of one footing, one single footing. So here you have the thickness, here you have the density, let us say 18 kilonewton per cubic meter. Here you will insert the pre-consolidation stress, 150, 200 for example. Here you will insert your CR. French engineers call this symbol CS, but I put it CR to be more universal, international. So 0.001. Here for example 0.15. Here 0.2. And here the initial void ratio 1.11 for example. Here you insert for example 3 and 3. Here the applied stress 175 for example, the embedment and the water level. So here you insert just the odometer results, and here the geometry of your footing, and you have now the odometric settlement along the footing width. Okay, now we will move to the estimation of the settlement of a group of footing. Okay, so just go here to footings group, short-term settlement. So what we have here you have the geotechnical data, okay, the thickness and the type of each layer. Let's say 5, 6 for example, the deformation modulus of each layer for example, and here the embedment to water table, the number of footing. Let us start by 4 footings, just 4 footings. So here you have the geometry of each footing. Okay, 2, 2. Here for example 3, 3, 2, 2 and 2, 2 for example. And here you will put the coordinates of each footing, 0, 0, 0, 2, 2, 0 and 2, 2. Okay, and here you will put the applied force, vertical force on each footing at the service limit state, SLS. In French we call it at ELS. Okay, so you can put here for example 1500, here 800 kilonewton of course, 1200 and let us say 900. Okay, and here we will see the deformation behavior of a group of 4 footings. So here in X and Y, the coordinates of each footing, you can insert them as you like. It doesn't matter if it's a closed surface or it's opened surface. GeoSpring take care of closing the surfaces and get the settlement distribution. So here it's like a 3D plot. Here we have the settlement 2.8 centimeter at the most loaded column, 0, 0. If you can see here at 0, 0 we have 1500. Okay, so actually geotechnical engineers would like to see the 2D distribution. It's more practical for them. So here we have the coordinates and the settlement distribution. So the most important value, it's about 2.8 centimeter, 2.9, and here you have just 1 millimeter. You can actually add, for example, let us say you would like to add a footing in the middle of this domain. Okay, so we change the number of footing. It will be 5, for example. So 1, 2, 3, 4, 5. Here we'll put 1, for example, and 1. Okay, and we'll put here, for example, 2200 kilonewtons. Okay, 220 tons. And here we'll have the 3D plot. Okay, here the most loaded area is the most loaded footing. It's at 1,1. So here you have distribution, 2D distribution. Okay, so actually this is the behavior of 5 footings group. This will be useful for you when you will, for example, study the behavior of a set of footings pertaining to a building built on isolated footing connected by beams. Okay, so it will be interesting to see the distribution of the short-term settlement beneath the foundation of the building. So we move now to the footings group behavior, the odometric settlement of a group of footings. So here it's similar to the other module, but you will insert here the odometric data. Okay, we insert here the pre-consolidation stress, 0.01, 0.02, 0.2, 0.2, and here the void ratio, 0.2. Here the embedment, the footing number, let us say 4, to accelerate the presentation. Let's take the same coordinates. Okay, I will take the same geometry, maybe change this one. So here let us put like this, and here 1300. So here we put it 4 footings, 00, 02, 20, and 22. Okay, and we confirm that the number of footings is equal to 4, and now we have the distribution of the odometric settlement along the loaded surface. Okay, so here it's like 3D and like this, it's in 2D. This is the distribution of odometric settlement. Thank you very much.